Hello, welcome to my talk all about the fluids. This talk is the second part of the talk on whether a viscous fluid could form a potential flow. This part will focus on the application using some interesting examples. As we know, for an incompressible rotational flow, the velocity potential function satisfies the Laplace equation. Under such an assumption, the last two terms related to the fluid viscosity in the Navier-Stokes equation will disappear automatically, even if the fluid is viscous. Since the dissipation term we can write as this, and you can see it is 0 for the incompressible rotational flow, and the compressibility term is 0 as well. This means that for an incompressible rotational flow, an inviscid flow is achieved automatically. However, for a compressible flow, the last two terms are not guaranteed to be 0. In the next few slides, some interesting examples would show that the inviscid fluids are not required in the potential flows. The first example is a uniform flow, which might be the simplest flow in fluid dynamics, but yet a very important flow in the potential flow theory. It plays a very important role in the fluid-structure interaction in the potential flow theory. The velocity potential function of a uniform flow is simply given as this, and the corresponding velocities are calculated using these equations. We can see there's only one non-zero velocity component, u, equals to the uniform flow velocity u0. And then we can easily to check the last two terms in the Navier-Stokes equation vanish for this simple uniform flow. As we can see this and this, and also we can have the core of the velocity vector is 0. For such a uniform flow, it is understandable there are no viscous force in fluid. It is because the gradients of the velocity components are all 0, even if the fluid itself is viscous. In this slide, we will see a very useful potential flow, a uniform flow passing a source, and we will see the interesting potential flow for such a combination. The overall velocity potential function is simply given by the superimposition of the velocity potential functions of the uniform flow and the flow from the source as this. In a polar coordinate, the potential function can be written as this, and we can check the velocity potential function satisfies the Laplace equation. Similarly, the stream function can be given as this, and if we draw the stream function of uniform flow passing a source, it can be seen that there is a bullet-shaped structure by the red line here. The red line actually separates the uniform flow and the flow from the source. That means there will be no flow across the red line. So the source in a uniform flow is equivalent to a bullet structure as this. The sides of the bullet structure is determined by the velocity of the uniform flow and the strength of the source. And we can easily check the last two terms in the Navier-Stokes equation as zero for such flow. Since the dissipation term, we have this, and the compressibility term, we have this. And again, in such a potential flow, there is no need to assume that the fluid must be invisible. In this example, we will see a mathematical beauty for the potential flow of a uniform flow passing a doublet. In the polar coordinates, the total velocity potential function is given as this, the superimposition of the uniform flow, this part, and the flow for the doublet, this part. And the stream function in the polar coordinates is given by this. And we can see on the circle the radius of the capital R. Here, the stream function is 0, is a constant stream function. That means the circle is a streamline of the flow. If we calculate the velocity component, the radial velocity component, and the tangential velocity component, they can be seen on the circle. The radial velocity component is 0. So if we draw the streamline of the flow, we can see the circle. The red line here separates the uniform flow and the flow from the doublet. We can also check the last two terms in the Navier-Stokes equation are 0, since these equations are 0. The uniform flows are very simple, yet very important flow in potential flows. However, in reality, we can only see few examples of natural uniform flow. For instance, the uniform flows generated in the test sections in wind or water tunnels. Otherwise, most flows are bounded with the boundaries. Having said that, we could have many equivalents for uniform flows in practical applications. For example, the aeroplanes fly in the calm air with the velocity u0. It is equivalent to that the plane is fixed and the uniform flow of velocity u0 coming to the airplane. This is the well-accepted principle for the wind tunnel or the water tunnel test and for the numerical modeling, in which the model or the airplanes are fixed and the incoming uniform flows are used. And we also see other similar applications. For instance, the objects fly in the air, the road vehicles running on the road, the trains running on the rails, the ship traveling in the sea. Another interesting uniform flow would be the sinusoidal flow, for which the velocity varies sinusoidally with time. If the dynamic system is linear, in such a linear system, the time factor in the dynamics can be omitted, and the dynamics could be transformed from time domain to frequency domain. Suppose in the time domain, we have a very simple potential function as this, and its velocity component u is calculated as this. In frequency domain, the corresponding velocity potential function is given by this. You can see the corresponding velocity potential function in frequency domain is the velocity potential function by omitting the time factor. Similarly, the velocity in the frequency domain is given by this. So we can see this velocity is a uniform velocity in frequency domain. For a reference, the first order and the second order differentiations with regarding time in time domain are given by this. In frequency domain, they are simply given by this and this respectively. You can see in frequency domain, the corresponding term can be obtained from the time domain by leaving the time factor out. In the next few slides, the potential flow theory is applied to ocean waves. For the linear ocean wave, the theory has been well established and widely applied in wave structure interaction, such as the ocean platform, ships, wave energy converters, and other floating and fixed structures under the action of ocean waves. The rotational flow for ocean waves might be different from many other problems since the flow is actually far away from the solid boundaries. It is especially true for the case in deep water. Hence, the flow can be regarded as an unbounded flow. For the linear wave, the flow can be regarded as an incompressible rotational flow which satisfies the Laplace equation, and the seabed boundary condition in deep water is given by this. We also have free surface boundary conditions. The kinematic boundary condition at the free surface and the dynamic boundary conditions, which is from the linearization of the Bernoulli's equation. Combine the kinematic and the dynamic boundary conditions, the ocean wave elevation eta can be given by this equation, where A is the wave amplitude, K is the wave number, and omega is the wave angular frequency. And also, by solving the Laplace equation and the relevant boundary condition, we can obtain the velocity potential function for the wave as this. This velocity potential function for waves in deep water. And we can calculate the fluid velocity from the velocity potential function, but we omit the time factor, so the velocity component u and w are given by this, and you can see the velocity component are the function of both z and x. And we also applied the dispersion relation for this velocity component. And based on the velocity component, we can calculate the gradient of the velocity with regard to x and z, given by this. And thus, the fluid stress or friction are given by this. So tau xx, tau xz, and tau zx, tau zz. Again, in all these expressions, the time factors are omitted. So, from these equations, we can see the shear stresses tau xz and the tau zx are actually the conventional fluid frictions. So the fluid frictions of the wave are proportional to the cube of the wave frequency, which means in high frequency wave, the fluid friction are larger. Based on the fluid friction, we can calculate the wave energy dissipation given by tau xz times u, which would be proportional to the quadruple of the wave frequency. And this may explain why the shorter waves are dissipated faster than the longer waves. And the stresses tau xx and tau zz are the normal stresses. And we can see there is a phase difference of 180 degrees between them. This is actually required by the condition of incompressible flow. All examples in this talk are unbounded flows, in which the inviscid flows can be satisfied even without the assumption of the inviscid flows, such as the uniform flow and the incompressible rotational flows. However, in reality, for the bounded flows, if the flow is viscous, the no-slip boundary condition must be applied, and it will cause a viscous boundary layer. The flow within the boundary layers are inherently rotational. Thus, the viscous boundary layer would be contradicting with the assumption of a rotational flow. Therefore, in rotational flows, no slip boundary conditions are not applicable. It should be mentioned that in the fluid structure interactions for potential flows, the solid boundaries are normally replaced by the singularities such as sources, doublets, and etc.